So let me go ahead and discuss a bit about what's coming up. So as a reminder, you have your exam on Friday. I will email I'll send out a reminder announcement with all the rules, but in general, open note, open book, and if you can access it via the Canvas course, that's allowed. You're allowed to use your IDEs on the exam. You're allowed to use any kind of software. You're allowed to do it on your own computer. You're allowed to use your own notes on your computer. What you're not allowed to do is go onto sites like Stack Overflow or, God forbid, sites like Chegg, and just a warning that the sites like Chegg, I've seen the answers they give when I was unable to really directly proctor students. They're wrong, and they're blatantly wrong in very interesting ways. So just be aware of that. Again, on Thursday, I plan on going over the practice exam. Again, the practice exam will send out an announcement. Maze solving is done soon. If you haven't done, and if we haven't started the maze solving, I need to adjust the due date on the recursion. I think that, let's see, October. When is that? October 14th? That seems a bit too far off. Let's see. So for recursion, yeah. That seems fine, actually. Okay. So for recursion, that's for week 7, but I know that some of you are already done with the maze, and so you probably want to get started with it. And it's worthwhile to know what's coming up. This is the second of the three big assignments I do. This one, recursion. So the solitaire encryption, if you did that, was a big one. Recursion puzzles is another big one, and then Cheater's Hangman is another one. If you had Professor Fiore, did he do Cheater's Hangman as well? Yeah. Well, guess what? You're going to do it again. Only this time you're going to do it better and way more in a way more interesting and involved way. Because at that point you probably knew how to use array lists, right? And that was about it. Or arrays, one of those two. Well, when we do Cheater's Hangman, we're going to use hash maps instead, and we're going to break everything down into word families so that it will successfully cheat and go and do so in an intelligent manner. All right, so with recursion puzzles, I like chess. It's a fun game. I like alternatives of chess even more so. For instance, I really enjoy playing a game called 5-dimensional chess with multiverse time travel, which is just kind of an insane chess game. See if I've got some of the pictures. Any of my pictures from here. But basically, yeah, it's chess, but with Terminator time travel mechanics. Very good game. If you're interested in making any kind of game, play this game because it's a very good exercise in how UIs need to be designed to be clear, even though everything is complex and with going on. Because you can check multiple kings across multiple timelines in the past and in the past. So it's a very interesting game. So it's worth playing if you're interested in designing video games. Even though it's technically 4-dimensional, but whatever. Okay. Recursion. So we've got a couple of classic chess problems. So the first problem is, as you go through the recursion modules, you'll learn a lot about recursion. And what we're going to be tackling is something called recursion with backtracking. Recursive backtracking is an extremely powerful problem-solving technique. In fact, it's pretty much depth first search, but we're using recursion here to do that depth first search. Except instead of having like a graph, you can see what we have are specific choices. I provided some pseudocode for you, and there's also more exercises there, what we'll see. But let me just go, sorry, and I give an explanation of how these problems are solved, and I'll go over more detail in these things. But let me just talk about the problems themselves. So you choose one of the two So there's 3 problems. You choose one of the 2 recursion problems here, okay? So why can't, where's the Zoom button? Oh, there it is. I feel dumb. Okay, so there's 2 recursion problems I've put in here. Sorry, 2 chess problems that can be solved recursively. You choose one of them, and then the other one is just writing a sudoku solver, okay? So let me tackle the first one, which is the 8 queens problem. Now, the 8 queens problem is a very old, very well-known problem, and it's been given as a computer science homework with recursion for years. Now, I should mention that I'm coming at this as though you have no experience with recursion. I know Professor Fiore does recursion, but if you've got transfer credits, you may not have tackled recursion, and that's okay. And even then, even if you did recursion with Professor Fiore back in spring, that was months ago. You know, you could probably use a refresher. So I go at this like you don't know what recursion is. Don't be too offended about that. So the 8 queens problem is fairly simple. I want you to place 8 queens on a board so that none of them can capture each other. Now, for those of you who do not play chess, you don't really need to know how to play chess in order to solve these problems. You just need to know how the pieces can move. The queen is the most powerful piece on the board. She's worth 9 points in terms of this. For instance, and the weakest piece on the chessboard is a pawn, and you have only 8 of those. So your queen is technically ostensibly worth more than all your pawns combined. The queen is powerful because she can move any number of spaces in any cardinal direction, north, south, east, west, and then any of those diagonals. So, and she can keep going until she bumps into a piece, which is what captures a piece in chess. So when we're saying to put 8 queens on a board so that none of them can capture each other, that means that basically we're asking to position queens in such a way that no queen shares the same row, column, or diagonal with each other. Make sense? As you can see, all these queens are in different rows, all these queens are in different columns, and they share different, none of them share any diagonals, right? None of them, right? This one doesn't have any diagonals over here that they can collide with. Now, if we look on Wikipedia, and believe it or not, again, Wikipedia is actually a great source for these kind of algorithmic things because they're not amusing enough to vandalize. And so this is the only symmetrical solution to the 8 queens problem. There are 92 distinct solutions. Although if you consider like rotations to be equivalent, so if you rotate the board and that looks like the same solution as something else, there's only like 12 different solutions. So those are the fundamental solutions, and they can all be rotated. So now what we can, so there's also variations, 8 queens, 9 queens, and 10 queens. Now the problem we're going to be solving is we're going to be using something called, again, recursive backtracking to solve this. And this differs from brute force. Brute force is basically the idea, let's try every single possible combination, okay? Now, unfortunately, that would take a really long time here because on the calculator, a chessboard is 8 by 8 squares, right? We have 8 pieces to place. So the first queen to place has 64 places to go, times 63, times 62, times 61, times 60, times 59, times 58, times 57. And I think that was what, so 64, 63, 62, 61, 60, 59, 58, 57. So yeah, that's how many, it's not a full it's a subset of the permutation operation, right? Because you only have 8 pieces to place as opposed to a 64. So, but that's a lot of solutions to check. That is in the hundreds of trillions. That's a lot for any computer. The thing is that a bunch of these solutions are dumb. Like putting a bunch of putting a queen here, if you put a queen on A8, right, A8 being here, and then you put a queen on AB on B8, you should be able to like trim off that whole branch. Nothing with a queen on A8 and B8 should be able to, should be checked beyond that. If you've already got two queens that, if you've already got an invalidation, you shouldn't need to check off the whole entire branch. And so that's what recursive backtracking does. It trims off entire branches so that you don't have to check things that you already know are going to be metaphorical dead ends for trying to find a solution. Does that make sense? Right? So the idea here is like, we know that this is going to lead to a dead end. I don't need to explore this path any farther. So that's why recursive backtracking is kind of a good way to do it. And as you can see, it's got an entire thing about exercise in algorithm design. It's a good example of a simple but non-trivial problem, meaning simple to understand, but non-trivial because it's not exactly super easy to do. So this is an illustration of how this is an animation of how recursive backtracking kind of works. We're basically replacing queens until we get to a dead end, and then we pick up queens to keep moving them forward. So you can refer back to that. But anyway, that's a pretty fun problem. The next if you don't want to do that problem, I've got a more challenging problem for you called the knight's tour problem, which is a knight. Now a knight moves in these L shapes. It moves one square in one dimension and two squares in the other dimension. So if he moves one square in the y-axis, he's going to move two in the x-axis. If he moves two in the y-axis, he's going to move one in the x-axis. So these are so here with these arrows, these are all the possible moves. And I actually programmed this in just a couple of lines in LaTeX to create this image. So that was pretty cool. So these are all the possible moves he can make. Now the knight's tour is another chess puzzle. In that one, you want to move the knight in such a way that you want to do a tour of the board, meaning that from his starting point, you want to move him around and make sure he touches on every square once and only once. Kind of like the Rudrata path problem we saw in exercise 3. So we want to move him, but it's not as simple as just moving him, side to side because he jumps, right? So the idea here is that that's the other thing about knights. They jump over other pieces. They jump from square to square because they're on horseshoes, and horseshoes can jump over stuff, So the idea here is that basically just make sure he moves into these squares and touch the squares and do the squares only once. You can start the knight wherever you want to, but basically you want to solve a problem. If you tackle that one, I highly recommend that. And the only reason this one's more difficult is because you have to check for out of bounds exceptions to make sure that your knight isn't going to jump off the edge of the board and into the abyss of null pointer exceptions, or index out of bounds exceptions rather. So that's the only reason it's harder. You got to make sure that you're not jumping off the board. So you can start it wherever you want. If you do this one, I highly recommend that you start with a smaller board, like maybe a 5x5 or a 6x6, rather than 8x8, just so that it will go faster. A solution shouldn't take that long though. Okay, so you're going to choose one of those two problems. The other one doesn't really have much of that, and that's Sudoku. And I'll go over this in more detail later on, but we want to write a program that can solve the Sudoku puzzle. Now, Sudoku, for those of you who are not familiar with that, it is a Japanese puzzle game. It is short for a digit single. Its full name is Suji wa Dokushin ni Kagiru, which translates to the digits must be single, where the digits are limited to one occurrence, and it's just simply abbreviated as single digit. And so there were variations of this. For instance, this kind of appeared in France in 1895, but it was popularized in Japanese newspapers. And then it spread out outside of Japan. Now, this is a typical Sudoku puzzle. Okay, and you can find these in newspapers. In fact, you can go onto the New York Times website right now and go to the Sudoku, just like you could go to their crossword puzzle, and they'll have puzzles for you every day to solve. So if you want to practice solving a Sudoku puzzle, you can. But this is what a typical Sudoku puzzle looks like, where you've got a 9x9 grid, and the grid is filled in with numbers from with different numbers. The numbers can vary from 1 to 9. The goal is that a complete board, a completed solution looks like this, where the red is the stuff that's put in. Every row has the number 1 through 9 only once. Every column has the number 1 through 9 only once. See, for instance, 9 only appears in this row once, and then this entire row down here, 9, 3, 5, 4, 7, 8, 2, 6, 1. Each number appears only once, right? So it can only appear once in a column and once in a row. But you also noticed that this grid of 9x9 squares is split into smaller grids of 3x3 squares, right? So we had 3 rules: one for rows, one for columns, but also one for the 3x3 squares. Numbers can only appear in the 3x3 square once. So 1, 2, 3, 4, 8, 5, 6, 7, 8, 9. So the top right 3x3 square only has the numbers appear 1 through 9 appearing once. So numbers can only appear once in the row, in the column, and in the individual 3x3 square. So for instance, if I go to the New York Times page over here, if I have a 1, so if I try to put a 1 here, it will mark that that's an error because I have a 1 already in this 3x3 square, right? I could put a 9 here because there's no 9 in this row and in this, in this row, in this column, or in this 3x3 square. So, and it becomes a logic puzzle of like, okay, and so the way we as humans, the only way we can reasonably solve this is a logic puzzle, which is, okay, for instance, I see there's a 1 here and a 1 here. So let's try to figure out where a 1 can go in this row over here. So we see a 1 in this 3x3, so we can't put a 1 here. There's a 1 over here, so we can't put a 1 here or here because, again, 1s can only appear in this 3x3 square. So the 1 has to go here by process of elimination because, again, on this bottom row there were no 1s. There's no we're blocked with 1s in this row, and then this 3x3, there's no 1s that can reoccur. And now that we know there's no 1s here, we also know there can't be a 1 here. There's no 1 there. So the 1 either has to go here or here for this column. Make sense? And so we just try to figure out, where our numbers can go from there. Oh, and we also know that a 1 has to go here because, again, same kind of logic. 1 here, there's a 1 here, and then there's 1 space left over. So that's how we would solve this as humans. Now in easy problems, they have they've got one possible solutions. In hard puzzles, you have to like kind of guess because you might have a potential thing, and then you have to backtrack if your answer is wrong. That is not how you'll do it with our solution. What we'll do for Sudoku. What to do for Sudoku is that you will do again, you're going to solve it in that kind of not quite brute force manner, because again, a brute force manner would be like, it would check all possible permutations, including ones that look like this. Right. And then it would check, this would be a valid thing to check in a brute force, as well as this, as well as this, as well as this, as well. Those are all wrong answers. You know, we could cut those all off because we already know that this first one we put was invalid. So we'll be using recursive backtracking to solve it, and we'll solve in less than a minute. That one has an accompanied extra credit, by the way. which isn't too bad. The extra credit is more Sudoku, just with file reading. The idea here is that with Sudoku, you will, there's a text file over here, in this over here, 6 kilobytes, and it's got, and what you're going to want to do is read this text file. It's got, these are Sudoku grids, as you can see, right? Just stored in a way that's friendly for the computer. You'll want to read all 50 puzzles and solve them. And the way you show that you've got it correct is by adding the 3-digit number at the top over here. For instance, this one is 483. The 3-digit number for this solution is 483. So sum together all those 3-digit numbers, and you'll get something in the 20, in the, like, I think the 24 or 27,000 range. And if you create an account for Project Euler, you'll be able to check your solution. You can submit it and it'll tell you whether it's right or wrong. But here you're just going to be solving 50 puzzles, and again, your computer should be able to solve all these puzzles in less than a minute, easily. So that will let you know if you've done your solution correctly or not. Okay, so that is all the stuff that's coming up for recursion. Any questions? Any other questions before I start taking demos and stuff? All right. Again, on Thursday, I will go over the practice exam in class. So, all right.